learning, please.
Hello? Hello, am I audible? Good evening everyone. Welcome to Goscore Learning. We are the fastest growing edtech industry in the Middle East and our main aim is to provide quality education for all. We are here to make your learning easy. I am Dhanya Rakesh, teacher from the Department of Chemistry, Goscore Learning. Today, I am here with the second part of Chemical Kinetics chapter, that is the third chapter of Grade 12 Chemistry. In the first part of Chemical Kinetics video, we have discussed about the introduction, the average rate and instantaneous rate, the order of a reaction and also the molecularity of reaction. If you are not aware about these topics, I have provided the link in the description box. You can go through it. So in today's session, we are going to discuss about the pseudo first order reaction as well as the integrated rate equation and half-life of a reaction. I know that the integrated rate equation is the most difficult portion that most of the students are facing difficulty in this particular chapter. Don't worry, today we can make it easier. Take a pen and paper with you. We can derive the equations for zero and first order reactions, and I have included some questions that we can expect from these portions for your upcoming board examination. So get ready with a pen and paper. Here we can start the second part of our chemical kinetics video. Are you all ready? Okay. So first we can start with the pseudo first order reactions. Okay. What is actually the pseudo first order reaction? You know that the word pseudo means, the pseudo means it's a false. Then what it is? It's a false first order reaction. Okay, that is the reactions which is not truly first order, but due to some certain conditions, it follows the first order reactions. Did you get any idea? No, right? Okay. So actually the pseudo first order reactions are not truly of first order, but if any of the reactant, if it is in higher concentration, see, take an example of reactant A plus B giving C. Okay. Here, if the reactant B is in excess quantity, it's in more concentration. Okay. Then, if you consider the rate of this reaction, the change in concentration of this B will be very negligible compared to the reactant A. Okay. So, here, due to the condition of excess concentration of one of the reactant, this reaction will follow first order reaction. That's why we call it as pseudo first order reactions. Okay? Because it's not truly of first order, but under certain condition, that is due to the presence of excess concentration of one of the reactant. Okay? Here due to the high concentration of this B, the reaction follows the first order kinetics. So when we write the rate law for this reaction, that is rate is equal to rate constant K into concentration of reactant. Here we will take into consideration of only the concentration of A. Why we are not taking the concentration of B? Because this is present in excess quantity and there will be only negligible change in the concentration of B. Okay, that's why we are not taking into consideration the concentration of B. Okay, so here when you see the equation, we may think that it follows higher order, but actually it follows first order. That's why we call it as pseudo first order reaction. It's due to the excess quantity of one of the reactant. That's why its change in concentration will be very negligible compared to the main reactant. Okay. Now you got the concept clear. What do you mean by the pseudo first order reaction? A reaction which is not truly of first order, but under certain condition becomes reactions of first order. That is what we called pseudo first order reactions. Okay. Now there are two examples which is provided in your reader and you should be very familiar with these two examples. That is the hydrolysis of ester, that is ethyl acetate, and inversion of cane sugar. So whenever you see these two equations, it should come to your mind that these are the examples for pseudo first order reaction. Now we can see the first one, that is the hydrolysis of ester. We will take the ethyl acetate. Okay, what's the formula for ethyl acetate? It is CH3COOC2H5. Okay, then hydrolysis means definitely there will be water, right? So here, when this ethyl acetate undergo hydrolysis, what the product we are getting is acetic acid and ethanol. Okay, so here the amount of this or the concentration of water will be excess. So when you compare the change in concentration of water with that of ethyl acetate, its change in decrease in the concentration will be very low. That's why we will not take into consideration the concentration of water while writing the rate law. So this reaction, you write the rate law, the rate is equal to rate constant K into concentration of ethyl acetate. Okay, so order is this, exponent is 1, so this is a first order reaction. So the first example for pseudo first order reaction, the first one is hydrolysis of ester or hydrolysis of ethyl acetate. Okay, now we can see the second example, that is the inversion of cane sugar. Okay, what's the formula for cane sugar? It's C12H22O11, right? So here for the inversion of cane sugar, what the product we are getting? It is glucose and fructose, C6H12O6 plus C6H12O6, glucose and fructose we are getting. Here also when you take the rate law, it will be K into concentration of cane sugar. So the two examples for pseudo first order reaction is hydrolysis of ester or hydrolysis of ethyl acetate and inversion of cane sugar. Okay, now the pseudo first order reaction is clear for you all, right? Now we can move on to the integrated rate equation. Okay, integrated rate equations that we know, it's different for different order of reactions. The integrated rate equation for zero order is different from that of a first order reaction. Okay. So, for you have to learn the zero order integrated rate equation as well as the first order integrated rate equation. First, we can see the zero order reactions. Okay. What do you actually mean by zero order reactions? Zero order reactions are that we already discussed in the part 1, right? Zero order reactions are those reactions in which the rate of reaction is independent of the concentration of reactant, right? So, if you take the reactant R changing into product P, if it is a zero order reaction, how we will represent the rate of the equation? Rate is equal to K into concentration of reactant with power 0. Any number raised to power 0, it is 1, right? So, here the rate of the reaction is equal to rate constant. That means, for zero order reaction, the rate of the reaction is not at all depending on the concentration of reactant. It is independent of concentration of reactant. Clear? So, these things is already you know that the zero order reaction means the rate of the reaction is proportional to the zero power of the concentration of reactant. That is, it is independent of the concentration of reactant. What you want to find out? We need to derive the integrated rate equation for zero order reactions, right? See. First, the integrated rate equations for zero order reactions. We can consider the reaction, that is, the reactant is changing into product. Okay. So, in terms of reactant, that is, the decrease in the concentration of reactant, how we can write the rate of the reaction? It is, rate is equal to decrease in the concentration of reactant with time. Okay. Since it is a decrease, minus the concentration of reactant by dt, right? So, as per the rate law, how we can write the rate? Since it is a zero order reaction, the rate is independent of the concentration of reactant. So, it will be rate is equal to K into concentration of reactant with power 0. That is, rate is equal to K. Okay. So, this is rate is equal to minus dr by dt, rate is equal to K. So, I can relate this to, right? So, it will be minus dr by dt is equal to K, rate constant K, right? So, if I rearrange this, I am taking this negative sign here and dt to the right side of the equal sign. Okay, then it will be, how I can write, dr is equal to, I am taking the negative sign there, then it will be minus K and dt, it will be into dt, isn't it? I can rewrite it like this. Okay. So, here we got the equation like this. dr is equal to minus K dt. When time t is equal to 0, what will be the concentration of reactant? It will be R0. That is the initial concentration, right? So, t is equal to 0. Concentration of R will be equal to R0. That is the initial concentration of reactant. T is equal to T. That is, at T time, what will be the concentration of reactant? We can represent it with R. R is equal to R is equal to RT. Right? So, if I am integrating this first equation with upper limit for reactant RT and R0, time T and 0, how can I write? It will be integral of lower limit is R0 and upper limit is T. TR, right? Integral of dr is equal to what? K is the rate constant. So, it will be minus k into integral of, what's the limit for time? 0 and t, right? Then it will be 0 to t dt. So, what is the integral of dr? Integral of dr, it will be, it is r, right? So, for integral, if we put the upper limit minus lower limit, how can I write it? It will be r t, that is the upper limit here, right? RT minus the lower limit R0. Isn't it? Integral of R0 to RT dr is, the integral of dr is R. So when you put the upper limit minus lower limit, it will be RT minus R0. Okay, is equal to minus K for T. The upper limit is T plus 0. It will be 0, right? So what you got here? RT minus R0 is equal to minus KT. This one I can rearrange or rewrite like this. It will be, if I take the negative sign out, I can rearrange it like this. R0 minus RT is equal to, what it is? R0 minus RT is equal to KT. I am taking the negative sign out. That means minus of R0 minus RT is equal to minus KT. Then I am cancelling the negative sign on the both sides. Right? So then the equation will be R0 minus RT is equal to KT. If I rewrite it, it will be R0 minus RT. I am taking the T on the left side, then it will be divided by T is equal to rate constant K. This is the integrated rate equation for zero order kinetics, right? See where R0 is the initial concentration of reactant, RT is the concentration of reactant at T time, and T is the time taken, K is the rate constant. Okay, so this equation you should by heart because it will be coming for the solving the problems. Okay, so I think this is clear for you. Now let's see how we will plot the graph for zero order reactions, because you should know clearly how we are drawing the graphs, because in the examination they will be providing the graph and you have to identify which order of reaction is this. Okay, which order this graph represents. Okay, so you're clear with the equation, right? And you should also keep in mind this equation also. This one will be useful for drawing the graph. Okay, that is RT minus R0 equal to minus KT. See, writing this equation here, that is RT, concentration of reactant at T time, minus R0 is equal to minus KT. This is what the equation we got while deriving the zero order reaction, right? So here, if you rewrite this equation, I can rewrite it like this. RT is equal to, I am taking this R0 on the right side. Then it will be minus KT. When you are taking this on the right side, it will be plus R0, right? Isn't it? So, what is this equation? It is a y equal to mx plus c. That is the equation for a straight line with y-axis RT, x-axis we are taking the time, and what's the intercept? M, that is minus k, negative slope. What's the y-intercept you are getting? R0. So when you take the reactant concentration at T time RT on the y-axis and time T on the x-axis, you will be getting a straight line with negative slope. That is the straight line we are getting with slope minus k. And when you extrapolate this graph to the y-axis, the point where the line coincides with the y-axis is the y-intercept, and that gives the value of initial concentration of reactant, right? So whenever you are getting a graph of reactant concentration at T on the y-axis and time on the x-axis, whenever you see this graph, you should identify that this is the graphical representation of zero order reaction with slope minus k and the y-intercept R0, initial concentration of reactant. Okay. So I think the first zero order reaction, integrated rate equation derivation and its graphical representation is clear for everyone. Now we are going to see few examples of zero order reactions. Okay. See what are the examples of zero order reactions. The first one is the some enzyme catalyzed reactions and certain reactions which occur on the metal surfaces are usually zero order reactions. And a very important another one example is the decomposition of gaseous ammonia. Okay, that means the ammonia when decomposes produces the nitrogen as well as hydrogen gas. If the reaction is carrying out at high pressure in presence of platinum catalyst, okay, if the reaction is carrying out at high pressure, usually this reaction when you balance the equation, it will be 2 and 3, right? So, this reaction, that is the decomposition of ammonia in presence of platinum at high pressure, it usually follows zero order kinetics. So, whenever you say this reaction, that is the decomposition of ammonia, it should come to your mind that this is a zero order reactions. Okay. And also the decomposition of hydrogen iodide on gold surface is also another example for zero order reaction. Okay, now we have learned the three examples for zero order reaction, that is the enzyme catalyzed reaction and reaction taking place on the metal surfaces. The second one and the important one is the decomposition of ammonia under high pressure in presence of platinum catalyst and also the decomposition of hydrogen iodide on gold surface. Okay, so with that we are finishing the integrated rate equation for zero order, that is the derivation as well as the graphical representation and three examples is for zero order reactions. Hope it's all clear for everyone. Now we are moving on to the integrated rate equation for first order kinetics or first order reactions. Okay, see. For the first order reaction, it is almost same like whatever we did in the zero order reaction. Same like we are taking the reaction of reactant converting to product. Okay. What we did for the zero order, same way we can represent the rate of this reaction in terms of reactant as rate is equal to what? Decrease in the concentration of reactant with time. That is minus dr by dt. Okay, as per the rate law, the rate of reaction will be rate is equal to, since it is a first order reaction, it is rate constant k into concentration of reactant with power 1 because it's a first order reaction. So it will be concentration of reactant raised to power 1. Okay, so when you relate this two equation, how we can write it? Minus dr by dt is equal to k into concentration of R, right? So, I'm just rearranging this equation, okay? I'm taking the R on this side and dt on the right side, okay? Then, and minus also I'm taking on the right side. It will be dr by R is equal to what? Minus I am taking on the right side, minus k, this dt into dt. Okay, I can rearrange this minus dr by dt equal to k into r as dr by r equal to minus k dt. Okay, and if it is for when t is equal to 0, what we told for the zero order, the reactant will be equal to R0. When t is equal to t, RT will be RT will be equal to R is equal to RT, right? R is equal to RT. Okay. Now, the same way what we did for the zero order, we want to integrate this first equation. Okay. When you integrate, how it will be integral? The upper limit will be RT and the lower limit will be R0. Thus, RT R0 dr by R, right, is equal to minus k. What's the limit for dt? It is 0 to t. Minus k integral 0 to t dt, right. So, what is this? Integral of dr by r. Integral of dr by r is natural log r, ln r, isn't it? So, when you write it in terms of upper limit minus lower limit, how we can represent it? It will be ln, upper limit is rt, ln rt minus lower limit is r0, ln r0 is equal to minus k first t dt, the upper limit is t, kt. Isn't it? So, keep in mind this equation. When you rewrite this equation by taking the negative side out, minus of ln r0 minus ln rt is equal to minus kt, right. So, this one, when you take the negative side on both sides, when you cancel it, we can rewrite it as ln r0 minus, ln r0 minus ln rt is equal to kt. Okay. So, how will you convert this natural log into log? That is, ln A is equal to 2.303 into log A. So, how we can convert it? It will be 2.303 into log R0 minus log RT equal to KT, isn't it? So, this one on the next slide, okay, one we can rewrite here what we got, 2.303 log R0 minus log RT equal to KT, right. So, we are writing it as 2.303 log R0 minus log RT is equal to KT. Got the equation that we got here, log R0 minus RT, log RT is equal to KT. Okay. So, this one, log A minus log B, what it is? It is log A by B. So, when you write it like this, it will be 2.303 into log R0 by RT equal to KT. So, in terms of the rate constant K, how we can write the integrated rate equation for K first order? It is K is equal to, I am taking the K in this side and T on the side, left side, then it will be 2.303 divided by T here, it will be divided by T into log concentration of R0 by RT. This is the integrated rate equation for first order reaction. Okay? That clear? what we did, we have done the rate equation. When you correlate it, we get it as dr by r is equal to minus k dt. When you integrate with upper limit rt and r0, we get it as ln natural log rt is equal to ln rt minus ln r0 equal to minus kt. Then you convert it into log by multiplying with 2.303. 2.303 log r0 minus log rt is equal to kt. Then when we are rewriting it, we got it as rate constant k is equal to 2.303 by t. T is the time taken into log r0. R0 is the initial concentration of reactant and RT is the concentration of reactant at t time. Okay, so this is the rate equation for first order reaction, and also you should be familiar with this equation also because this will be useful for drawing the graph. Okay, so when you take this equation, first we can go for this one. We will be looking for the graphical representation. What we got the rate equation for first order reaction? It is rate constant k is equal to 2.303 by T into log concentration of R0 by RT. Right? Now, I am just rewriting this equation. Okay? And keeping this log R0 by RT here. Log by T is equal to what? K into T by 2.303. Isn't it? So this one I can just rewrite it as log R0 by RT is equal to K by 2.303 T plus 0. Okay, then it will be y is equal to mx plus c. What is in the y-axis? It is log R0 by RT. When you take the constant log R0 by RT on the y-axis and T on the x-axis, okay, what will be the line you are getting? See here, the y-intercept is 0. That means we will get a straight line which passes through the origin. So your line will be like this, that the line passing through the origin with a slope. What is the slope? M K by 2.303. Okay. So whenever you got a graph like this, that the graph passing through the origin and y-axis we are plotting the log R0 by RT and in the x-axis it's time, then you should know that this is the graphical representation of a first order reaction. Okay. And also we can draw one more graph. That's I told you. You should keep in mind this reaction also. This equation also, that is ln RT minus ln R0 is equal to minus KT, right? This is what we got here while deriving the equation. ln RT minus ln R0 is equal to minus KT. That is the same thing I rewrite here. Okay. So, this one also when you rewrite it, ln RT is equal to minus KT plus n 0. And that, so that is y to x plus c. What we are taking on the y-axis? It is ln RT. Okay, what on the x-axis? It is time. And here y-intercept is ln R0 and the slope is minus k. So you are getting a line with negative slope like this. That slope minus k. And when you extrapolate the graph to y-axis, the point where the line coincides with the y-axis is the y-intercept, that is natural log 0. Okay. Same way, if you are taking log RT in the y-axis and time in the x-axis, how will you the graph? You will get the graph same like this, but what will be the slope here? The slope will be equal to minus k by 2.303, right? Because this 2.303 came when we convert the natural log into log. Okay, and your y-intercept will be, in that case, if you are taking log RT versus T, then the y-intercept will be log R0. Okay, so these are the graphical representations for first order reactions. Okay, so I hope that derivation as well as the graphical representation is clear for everyone. Now let's see few examples of first order reactions. Okay, the examples for first order reaction. The first one is the hydrogenation of ethene. Ethene hydrogenation is an example for first order reaction, as well as the second one is the natural and artificial radioactive decay of unstable nuclei. That's also another example for first order reaction. And the third one is the decomposition of N2O5 and N2OR, another example for first order reactions. Okay, so these are the different examples for first order reaction. So we have done the derivation, graphical representation, as well as the example for first order rate equations. Okay, so now we can move on to some problems related to topics that we covered till now. Okay, before that, there is one more thing, that is the gaseous first order reaction. That is, until now we have described the terms as in terms of molar concentration like that. If it is a gaseous reagent, how we will find out the rate constant? That is, if A gas is converting into B in the gas form plus C in the gas form, how we will find out the rate of the reaction? For that kind of gaseous reaction, we will find the rate or the rate constant. We will write the rate constant as K is equal to 2.303 by T into log Pi divided by 2Pi minus Pt. Now what is this Pi? Pi is the initial pressure exerted by the reactant. Okay, then what is this Pt? It is the total pressure exerted by the gases. Okay, so for gaseous reactions, you can write the rate of the reaction by using this equation. Okay, now let's see some problems related to topics that we covered till now. Okay, that is, the first one is the decomposition of ammonia, that we already told it is a zero order reaction, right? So the decomposition of ammonia on platinum surface is a zero order reaction. It's clearly mentioned that it's a zero order reaction. So order will be 0. Okay, and if the rate constant K is provided in the question as 4 into 10 the power minus 3 mole per liter per second. Okay, mole per liter per second. Now, what you want to find out, how long it will take to reduce the initial concentration of ammonia from 0.1 molar to 0.06 molar. That means the initial concentration is, whereas the initial concentration R0 is from what? It is 0.1 molar, right? And R0 will be 0.1 molar. Is the final concentration? It is 0.06 molar. RT is equal to 0.064 molar. You want to find out, you want the time taken for this reduction of concentration from 0.1 to 0.064 molar. Okay, so time we want to find out. How we will find out? For zero order reaction, what is the rate? How we will find out the rate constant? K is equal to, for zero order reaction, it is R0 minus RT divided by T. Here the rate constant is provided, R0 is provided and RT is provided. What you want to find out is the time. Okay, so it will be T is equal to R0 minus RT by K, right? So substitute the values there. R0 is 0.1 minus 0.064 divided by what is the K value? It is 4 into 10 the power minus 3. Right? So 0.1 minus 0.064, it is 0.036, right? Divided by 4 into 10 the power minus 3. So, what will be your answer for this one? It will be 0.009, right? So, we can write the answer as 0.009 divided by 10 the power minus 3, that is into 10 the power 3. So what will be your answer? It will be 9. What is the unit? It is the time and the unit will be in second. So your answer will be 9 seconds, right? So, whenever you are provided with the initial concentration and final concentration, if it is a zero order reaction, the only thing you want to know is to remember the rate equation. Know the equation, just simply by substituting, you can easily score the mark. Okay. Now, let's see another example. Here, the rate constant for a first order reaction is 60 second inverse. How much time it will take to reduce the concentration of reactant to 1/10th of its initial value. Okay. So here the rate constant for first order reaction is given as K is equal to, right here, the rate constant K is equal to 60 second inverse. Okay, it's a first order reaction. Okay, how much time it will take to reduce the concentration of reactant to 1/10th of its initial value. So if you are taking the initial value as R, we can take it as R, and what is the final value? RT is 1/10th of initial value, that is 1/10R, right? This is the 1/10th value of the initial value. Okay. So what you want to find out? You want to find out the time. What is the time taken for this reduction from 1/10th of its initial value? Okay. So for first order reaction, what is the equation? K is equal to 2.303 by T into log concentration of R0 by RT, right? So here the rate constant is provided and we want to find out the time. Okay, so how we can write it? T is equal to 2.303 by, what is the rate constant value? K value. I'm taking the T here and K here. Okay, it will be 2.303 by 60 into log concentration of R0. It is R by 1/10R. So this R and this R will be cancelled, and what we will be getting here? It will be log 1/1/10. That is equal to, this will be coming on the numerator. It will be log 10, right? Log 1/1/10 is log 10. What's the value of log 10? It is 1, right? So how we can write it? Is 2.303 by 60 into log 10. Log 10 is 1. So we want to find out only 2.303 by 60. Okay. So if you do the calculation, 2.303 by 60, how it will be? 0.0. Then it will be 3 6 are 180. Okay. 8 6 are 480, right? So we will be getting 0.038. 0.038, or I can rewrite it as 3.8 into 10 the power minus 2. That much seconds will be the answer. 3.8 into 10 the power minus 2 seconds. Okay, so for this kind of questions, the only thing you should know is, here we are taking the 1 by 10th of the initial reactant, so it should be 1 by 10 R. So if you know the equation for first order reaction, simply by substituting we can do the calculation. Okay, now let's see one more example, that is, for a first order reaction, show that the time required for 99% completion of reaction is twice the time required for the completion of 90%. So for percentage decomposition, we can use the equation, that is K is equal to 2.303 by T log A by A minus X. Here A will be, if it is in percentage decomposition, A will be 100 and X will be how much it got decomposed. Okay. So here for this question, how we can write? It's a first order reaction and the time required for 99% completion. Okay, that we need to find out the time. T is equal to 2.303 by K into log what? A is 100 by 100 minus, it is for time for 99%, right? So X is 99. So we can write it as 2.303 by K into log 100 by 100 minus 99 is 1. Then it will be log 100, right? So 2.303 by K, I can rewrite this log 100 as log 10 raised to 2, isn't it? So it will be 2.303 by K into 2 log 10. Log 10 is 1. So it will be 2 into 2.303 by K. Okay. Now you got the time for 99% as 2 into 2.303 by K. Okay. Now let's see for the 90% decomposition. Okay. So for T 90%, how it will be? It will be 2.303 by K into log 100 minus, what is the value of X here? It will be 90, right? So what will be our answer here? 2.303 by K into log 100 divided by 100 minus 90, 10. Then it will be 2.303 by K into log 10. Log 10 is 1. Then it will be 2.303 by K. See, for T 90%, it is 2.303 by K, and for T 99%, it is 2 into 2.303 by K. That's what we want to prove in the question. We want to prove that the time required for 99% decomposition, completion of first order reaction, sorry, not decomposition, it's the completion of first order reaction is twice that of the 90%. See how easy it is, isn't it? If you know this equation, just simply substituting that value, you can easily solve the problem. Okay. Now we can move on to the another very important portion in this chapter, that is the half-life of a reaction. Half-life is nothing but the time taken to reduce the initial concentration to half of its value. Okay. So if you are taking a full plate full of food, what the time you taken to reduce it to half of the value? That is what the T half. Okay. The half-life of a reaction, half-life we represent by T half. Okay. T with the subscript half. The half-life of a reaction is the time in which the concentration of reactant is reduced to 1/2 of its initial concentration. If your initial concentration is R0, the time taken to reduce its concentration to R0 by 2. That is what the half-life of a reaction. Okay. Now let's see the half-life of reaction for zero order reaction. Okay. So what is our equation for zero order reaction? K is equal to R0 minus RT by T, right? Isn't it? So we can write it in terms of T as R0 minus RT by K, isn't it? So when time T reduced to half, that means the concentration, what is RT? It will be half of the initial concentration, that is RT is equal to R0 by 2, isn't it? So when I substitute this RT equal to R0 by 2 in this equation, what I will get there? It will be time is now half time, T half. Okay, T half is equal to what? R0 minus, what is RT now? R0 by 2. Isn't it? At half time, RT will be R0 by 2 whole divided by K. Okay. Then T half is equal to R0 minus R0 by 2 is 2R0 minus R0, that is cross multiply. 2R0 minus R0 by 2, that is R0 by 2 K. See, this is the half-life of a zero order reaction. See, for a zero order reaction, the half-life is directly proportional to initial concentration of reactant. I am repeating, for a zero order reaction, the half-life of the reaction is directly proportional to initial concentration of reactant. Okay, so keep in mind that for zero order reaction, the T half is directly proportional to the half-life of reaction. Okay, so T half for zero order reaction is R0 by 2K. Now we can see for the half-life for first order reaction. Okay, same like here. For first order reaction, what is the equation? K is equal to 2.303 by T into log R0 by RT, right? When T is equal to T half, then what will be the RT value? It will be same like what we done for the zero order. It will be half of the initial concentration. Then it will be R0 by 2. Substitute the value in this equation. Then we can write the T half as T half is equal to 2.303 by K into log what? R0 by, what is the value for RT? It is R0 by 2, right? It will be R0 by 2. So this will be like be getting cancelled. Then how it will be? 2.303 by K into log 1 by 2, that is log 2. What's the value for log 2? It is T half is equal to 2.303 by K into value for log 2 is 0.3010. Then it will be, when you multiply it, you will get the half-life of first order reaction as 0.693 by K. See, for a first order reaction, the half-life is all depending on the concentration of reactant. Okay, so for first order reaction, the half-life is not depending on the concentration of reactant, and for zero order reaction, the half-life will be directly proportional to the initial concentration of reactant. Okay, so we can have some problems as related to this. This is simply by substituting the value, that is the first order reaction, the rate constant, it is given as 5.5 into 10 the power minus 14 second inverse. And what do you want to find out? Half-life. For half-life, it is simply by substituting the value in the equation. 0.693 by K. If you put the value here, you will get the half-life for this reaction. Okay, so what will be the unit? It will be in second. When you do the calculation by substituting this, you could easily solve this, right? And same like here also. See, the question is coming in a different pattern, like it is the first order reaction takes 69.3 minutes for 50%. That is T half, it is given as 69.3 minutes. Okay. So what you want to find out, 80% of the reaction will completed at what time? Okay. So here T half is provided so that we can find out the K value, right? K value will be 0.693 by T half. That is 0.693 by 69.3. That it will be 10 the power minus 2. Minus 2. It is in minutes, so will be minute inverse, right? So now what do we want to find out? The time required for 80% of the reactions to get completed. So for percentage decomposition, what we will do? K is equal to 2.303 by T into log A by A minus X. Here we can give T. K value we got, so T we want to find out. T is equal to 2.303 by K will be 10 the power minus 2 log what 100 by 100 minus 80. Then it will be log 100 by, here we will get log 100 by 100 minus 80 is 20. Then it will be log 5. By substituting the log 5 value is given in the question. So by substituting this 2.303 by 10 the power minus 2 into log 5 value 0.6990, you will get the answer and your unit will be in minutes. Okay, because in the question it's given in minutes. So your final answer, don't forget to write the unit in your final answer. Your final answer after doing the calculation will be in minutes. Okay. So I hope this portion is clear for everyone. And we have the last question, that is the predict the order of reaction. By seeing this graph itself, here y-axis it is T half and in the x-axis it is R0. So here you can see that the T half is not at all changing with initial concentration. That means it is independent of initial concentration. Which equation is independent half-life? That's this indicated first order reaction, right? So here the K is equal to 0, T half is equal to 0.693 by K. That's why we are getting a graph like this. So here for the second question, see the direct half-life is directly proportional to initial concentration of reactant. So what it will be for zero order reaction? What is the T half value we are getting? T half is equal to R0 by 2K, right? See here the T half is directly proportional to initial concentration of reactant. So this will be the graphical representation of a zero order reaction. See how easily we find out it, right? So I hope the pseudo first order reaction as well as the integrated rate equation for zero order and first order reaction and the equations for finding out the half-life of a reaction and the problems related to that are clear for everyone, isn't it? So I will be coming with the third part of this video in the next coming week. And also one more thing, that your Satin sir will be coming with some sure short questions from your Maths chapter Continuity and Differentiability on the 20th September Wednesday. So don't forget to subscribe our channel and stay tuned for our live videos. Thank you.